Alright, here is our last video of the unit with which I will be reviewing the unit. So, here is the formula sheet that you are going to be getting for this. Actually, you know what? I changed my mind. I'm going to add some more to this. I just decided I'm going to do this right now, so, see. I'll add the series rules for the series and parallel rules for voltage and current. Okay, and then I total equals 1. Like that. Okay, and you know I could actually just put the resistances and stuff in there too. I don't think I want to. I don't want to mess up the formatting though, so it's fine. And then in parallel, you spell total. The V's are equal. And I total, they are additive. Okay, and just to space this out a bit better, I'll do that. Okay, so, alright, you know what, I'll get there. Looks slightly better than it was otherwise. Yeah, so here's what we got. Okay, so you have K, 9 times 10 to the 9, and then I give you the charge. So here, Q, remember Q is charge, so QP, that's P there, is your charge of a proton, which is this. And here's QE, so this is your charge of an electron. Again, it's the same thing, just one's negative, no, it's positive. I'm also giving you the mass of a proton and the mass of an electron, if you need those for whatever reason. For example, remember there were some questions where it was like, oh, from you get voltage, right? And then from voltage, you get potential energy. And then from potential energy, you turn into kinetic energy and you solve for velocity. And to do that, you need a mass, right? So that's why I'm giving you those masses. And you might need it for some other thing too, but, you know. And then here's your main equation. So here's your electric field equation, that E is kq over r squared. Remember, E is the field. I know it's kind of confusing, but that's the letter that's used. And the units for the field is newtons per coulomb. And then the force is a different q times the field strength. And this is also clarifying, say, hey, there's one q that's starting the field and the other q that's in the field. And this is also, so kq over r squared, this is used if you have just two charges and you want to know what is the force between them. So if that's the question, what is the force between these two charges, then you can just go straight to kq over r squared. Otherwise, I would definitely find the field first and then get the force from that. Similarly, we then have the voltage, this is kq over r, and that's in volts, and the potential energy, which is the different q times v, and again, same kind of situation. You could have a question where it's like, here's two charges, what's the potential energy between them? And you can figure it out that way and go that way. But otherwise, I would definitely solve for voltage first and then go to potential energy this way. And again, potential energy is in joules. And then clarifying that it's the scalar, so voltage and potential energy are scalars, while the electric field and the force are vectors. And then we have the circuit rules, right? V equals IR, and then your R part in series is you just add them up, and your R part in parallel, you do 1 over the total parallel equals 1 over, you do the 1 over sums, and then 1 over at the end. And then here's your series and parallel rules for voltage and current. So if you have a circuit that's in series, the voltages on each resistor add up to the total, and if they're in, and their currents are all equal to the total. In parallel, the voltages are all equal to the total, and the currents are summative to the total. So that's what you got for this unit. You shouldn't need anything else up here. The only thing, I mean, okay, I have these numbers up here as well, but, you know, we have them down there. So besides that, you shouldn't need anything else. I don't think so anyway. So yeah, that's what we got. So let's go through some examples here. So the main kind of questions, again, remember the unit's kind of split in half, right? You have the electric field and voltage stuff, and they have the circuit stuff. So I'll kind of go through, I'll go through 3 questions. So the first, let's do a field question. So let's say, let's see. You have a, I don't know, plus 10 microcoulomb charge that's 1 meter to the left of a minus 5 microcoulomb charge. What, let's do first question, say A. What is the total electric field strength 1.5 meters to the to the right of the minus 5 microcoulomb charge? Okay, so that's what we're going to start with first. Now, since this test is online and you can use resources, definitely you can use the labs to your advantage to sort of figure stuff out. So, of course, there's the circuit lab and there's the electric field lab. So this is definitely electric field questions. So let's kind of use this to help figure this out. Now, I'm not going to, of course, build this one-to-one because plus 10 microcoulombs, that means I have to put in 10,000 charges because, again, they're nanocoulombs. But I will... This one is twice the strength of this one, right? Because this one is supposed to be plus 10. This is minus 5, so this should be twice the strength. Like that. Okay, and we want... I said they're 1 meter apart, right? Yeah, it's 1 meter to the left. Okay, so this... You can see this lines up. That's 1 meter, so that lines up like that there. So I want the field strength that's half a meter to the right of the minus charge. So that's going to be here. Okay, now again, this number is not going to be accurate because these numbers are not accurate either. So, but it gives you an idea. Okay, so let's see if we can kind of solve this and see what we get. So, how this works is we are going to solve for the fields independently. Okay, so there's a field caused by the positive 10 charge and the field caused by the negative 5 charge. So we're going to solve for those independently. So let's see, the field strength for the first one is KQ U1 over R1 squared. So K is 9 times 10 to the 9 times Q1. So that's going to be 10 times 10 to the negative 6 because the microcoulombs. And again, this ends up just being 10 to the minus 5, so I'm going to get rid of that. Divided by distance squared. Now, the distance here, we are half a meter to the right of the minus 5 charge, okay? So, the distance we want, though, is the distance from this one, okay? So that's 1 plus half, so it's going to be 1.5 meters squared. So what does this end up equaling? 9 times 10 to the 9 to the 5 is going to be 9 times 10 to the 4. Oops. Divided by 1.5 squared, which is... oops, over there. Back over here. Okay, 1.5 squared. Wait, it should just be 2.25, right? Yeah, 2.25. Okay. So, 90,000 divided by 2.25 gives you 40,000. Okay, so... And what's the direction of the field? The direction, it's from the positive charge. So remember, the positive charge, the field goes outward. Okay, so the field goes outward from a positive charge. So, since we're to the right of it, yeah, we're over here. Again, this positive charge, the field from this positive, again, I know that this arrow is pointing to the left, but the field just from this charge is outward. So just from this charge, the field is to the right. Okay, now E2. Is the same as always. Okay, and now our charge is 5 times 10 to the negative 6. Now you might think, ooh, what about the negative? The negative just handles direction, okay? So the negative is going to be taken care of once we figure out the direction, so don't worry about that. Now the distance here, it's just to the right, 0.5 meters to the right of this. So we are now 0.5 meters from that. So we have, multiply this together, so this is going to be 45 times 10 to the 3, which I'll just keep like that for now, even though that's incorrect. and then divided by 0.5 squared, which is going to be 0.25. So this gives us 45,000 divided by 0.25, 180,000. And that's to the left, okay? Reason it's to the left is because now we have it's a negative charge. It's pulling the field in towards itself. So since the field's pulling it in this way, that means from this negative charge is pulling into the left. So the total field, they're in opposite directions. This one's bigger than this one. So the total is going to be 180,000 minus 40,000, and therefore the total field strength is going to be 140,000 newtons per coulomb to the left. Now again, we can't really see that from the numbers here. We can get to, like, if we get it right, you see this is about like 28 or so, close to 28 if we get it right. So the numbers, again, so 28 to 140,000, this is 5,000 times bigger than that, 50,000 times bigger than that, and whatever. It's right, okay? This number is correct. So that would be your total field strength at that point. So a second question could be, what would the force be on a, let's say, -2 microcoulomb charge at this position? Okay, so for force, you take this new charge and you're multiplying it by the field strength. So the new charge is the -2. Again, ignore the negative because that will be dealt with when we deal with the direction. Times 140,000. So that's, so minus, okay, so times that 0.28. And which direction is it? Well, the field strength was to the left. And when you're multiplying a negative charge for the force, the direction of the force is opposite. Okay, so negative charges follow the field. No, positive charges follow the field. Negative charges go opposite the field. So this is a negative charge, so it would be moving to the right. And if you think about that, it makes sense. If you have a negative charge right here, well, it's right next to a negative charge, and two negatives, if they're the same sign, then they want to go away from each other. So this charge will want to go to the right. Okay. Now, follow-up question. Same setup as before, but now, what is the total voltage? Okay, so it's the same question, but now we want the total voltage. Let me put that down. Okay. So do the exact same thing. We want to do the voltage from the first one and the voltage from the second one separately. So again, this is all the same. Keep doing that. And the charge 1, again, this is your 10, your positive 10. So let's just jump ahead and say 10 to the -5. And then divide it by, and again, it's the same distance, 1.5, but it's not squared this time. So we end up with 9 times 10 to the 4 divided by 1.5. And that will be 60,000 volts. Okay. Now V2. Now here, this is where you do put in the negatives. Okay, because before the negative just dealt with direction, but there's no direction to voltage. It's just, is it positive or is it negative? So we have -5 times 10 to the -6 divided by 0.5. So we get -45 times 10 to the 3 divided by 0.5. So 45, 1, 2, 3, divided by 0.5. So it's that's the negative of this. So what's the total voltage? Now it's always just V1 plus V2, which is 60,000 plus -90,000. So our answer is -30,000 volts. And we can check this if we turn voltage on. And do we want to put this in here? -6. Well, it is negative, so that should definitely be the same, just because our scaling is off. But yeah, so -6 compared to -30,000. Again, trust me that it lines up, so it does make sense that that's the answer. Okay, and then again, follow-up from this is now, what would the potential energy be on a -2 microcoulomb charge at this position? So, same exact setup. It's this new charge times the voltage. So we have -2 times 10 to the -6 times -30,000. That easy there. Okay, times 0.06. That's your answer for that. Notice we have, again, negative times negative, it cancels out. When you get to the potential energy, like the actual answer for the potential energy, it doesn't really matter if it's positive or negative, because what's negative potential energy? It's like nothing really, right? It doesn't really mean anything. The distinction here is not important, okay? So for voltage, it matters, because for voltage, then you're dealing with how do positive and the negative charges react in that sense. But once you get to the energy, you've kind of dealt with that, and you said, okay, you're getting this number, and it doesn't really matter in that case if it's positive or negative. So, yeah, so that's sort of the answers that you get there, and you should kind of work through this through. The only time, again, that I would say if you really want to, like, jump to the force or the potential energy is, for example, let's say, what is the potential energy between a +10 microcoulomb charge and a -5 microcoulomb charge? Okay, if you just get it, if you get a question just like this, or again if it's force, then I would say, okay, you can do this kind of equation. And this would be 10 to the -5 times -5 times 10 to the -6 divided by, oh, that are, I have to get distance. I'll just keep that are 1 meter apart. There, make it easy. So equals divided by 1. In this case, we have, so -45 is 9 times -5 times, so we have 10 to the 9 times 10 to the -5, which would give me 10 to the 4, and then 10 to the -6, which is, or 6, this is times 10 to the -2. And since it's -45, this becomes 4.5 times 10 to the -1, right? Hold on. Yeah, okay. Making sure I'm doing this right. Or, so 0.45 joules. And again, the negative here, it's like, what is it? It doesn't, you don't need it in this case. So in that case, you can jump straight ahead. Now notice, this is not the same kind of question that we did before, right? So don't confuse doing this with like going through what this question was asking. So you can't just jump, because you might think, oh, well, I have a -2 microcoulomb charge, and I have the 5 and the 10, so I could do it. Just don't, it makes it more complicated, okay? just don't do it that way. So it's much easier to make a mistake and do something accidentally and stuff. So work through the full voltage to potential energy process or the electric field to force process, unless the question is very specific. You have 2 charges, they're this distance apart, what is the force or what is the energy? That's it, okay? Otherwise, don't really worry about it. And you could have a question that's sort of an opposite. So remember, here's sort of a second question, right? Let's see. You have an 18 volts battery that is, I don't know, how long are those batteries? 5 centimeters long. So first question, what is the charge in the battery? Okay, so this comes from V equals KQ over R. But the thing is, we know what V is, we know what K is, because it's K, and we know what R is. That's, in this case, going to be the 5 centimeters. So we can solve for Q. So we have 18 equals 9 times 10 to the 9 times Q. divided by r. Now it's 5 centimeters, so it's 0.05 meters. So this means we have Q equals 18 times 0.05 divided by 9 times 10 to the 9, which is a small number. Whatever the heck that is. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's 10 to the negative 10 coulombs. Okay. Yeah. So then, again, a follow-up question for this could be, what is the potential energy of one electron in this battery? Okay, so remember, potential energy is this new charge times the voltage. So what is the new charge? Well, I'm saying, what is the potential energy of one electron? So that's sort of the new thing I'm throwing in there. I'm throwing in that new electron. So I want the charge of one electron. And again, as I said with this, once you get to potential energy, the negative positive doesn't really matter. That's the charge of one electron times the voltage of 18. 1.6 times 18 gives you that. So it's going to be 2.88 times 10 to the negative 18 joules. Yeah. That's my potential energy 1 electron. And then you could say, okay, how fast would the electron be moving once this battery is connected to a circuit? Okay, and so here the question is really, we have a potential energy, and we're saying this potential energy is now getting converted into kinetic energy. And then that kinetic energy is, well, 1/2 mv squared. Oops. So 1/2 times them. Now here's our mass comes into play, right? Because again, this would be the mass of the electron. Where's the point? 0.11. Here's you get to some kind of gross exponential stuff. Okay, so v squared, you gotta multiply 2.88 times 2, so it's gonna be 5.76. 5.76 times 10 to the negative 18 divided by then the mass. So what is that going to equal? 5.76. Let's see. Okay, divided by 9.11 is that. I'll say 0.6323. Okay, times, and then negative 18 minus negative 31. So, in other words, 31 minus 18, 13. Which therefore this means this is that. So then we got square rooted. So okay, we got, hold on, let me 5.76 divided by 9.11 is that, wait, what? 5.76 divided by 9.11. There we go. That times 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Doop. You get that, and then you gotta square root it. Square root. Where's the square root? Oh, I got a second. Okay. That. So my answer is 2.5145. There's my answer. Yeah, so again, that's kind of, this is probably the grossest thing in terms of the math and going through stuff. Yeah, but again, it could be something you could be asked about. And again, this remembering also this whole idea of like finding charge from a voltage. And actually, you could actually find charge from also the field. If I say, hey, the field strength is this from a charge, therefore, if I'm this distance away, therefore, what is the charge? You could also do it for like forces. Like for example, let's say you have two charges, and let's say they're equal charges. Otherwise, you can't really do this. So let's say you have one charge. It's you know I don't know. We don't know what it is. Okay, you know these. You have two charges, and they are at equal. Uh, they have an equal charge, and there's distance of blah between them. Okay, and if you know what the force is between those two charges, you could then work this out, right? So for example, and again, it's not really technical, but let's say if you have right, this is if you have two charges and you want to know the force between them. Well, if you know that the two charges are equal, then you can just change this to q squared. And then if you know what r is, you know what the force is, then you could sort of say this, well, q squared would equal f times r squared divided by k. And if you know what all these numbers are, then you can solve for the charge and then square root it, and you could get your charges. Okay, so again, you could kind of this idea of solving charges from the other numbers. You can actually do that, and it's possible. So just think about that. But that's kind of a rare example. But anyway, okay, let's do a circuit question. Let's do something a little bit complicated. So not insanely complicated, but a little bit complicated. So how about let's do. I know. I'll build this and I'll see. Let's do okay. Have that. And do that here. And then I'm gonna make up let's say that. Let's say this one is 5. Trying to be nice here. Okay, so that'll be 5. Let's have this one be 4. Let's put one here, and let's have this one be 2. And then let's have the one down here. Have this one be 9. And then we can connect these. And that. That. And there we go. Okay, so we got a circuit. So my question is going to be basically like the circuit worksheet. Okay, so you have that circuit where we have let's see, we have R1. Let's say R1. Let's just kind of go in order. So say R1 is the 5. We have R2 is, let's say it's the 4. Let's say R3 is the 2. And let's say R4 is the 9? Yeah, 9. And then we have our total over here. However, we also want I1, we don't know. I2, which we don't know. And I3, which we don't know. Oh, and I4, which we don't know. And we want I total. And put in the V. We know V total, that's 9 volts. Yeah, okay. So, we want to try to solve for everything else here. Now, the first step is figuring out the total resistance. Okay, so in terms of how the circuit is set up, we have R2 and R3 are in series. Together, they are in parallel with R4. Together, all three of those are in series with R1. Okay, so that's sort of the description of how that works. So we have the total. Well, hold on. So R2 and R3 are in series. So R23 is going to be R2 plus R3. Okay, we can definitely solve for that. R2 plus R3, so that's 4 plus 2. So it's going to be 6. Now, those two are then in parallel with R4. So this means 1 over R234 equals 1 over R23 plus 1 over R4. So we have 1 over 2, 3. So it's 1 over 6 plus 1 over 9. So let's see. How can we simplify this? Well, 18 works. So this is going to be 3/18. And this is 2/18. This is 5/18, which means R234 is 18/5, which is 3.6. Oh, yeah, the equal defaults. Yeah, 3.6. Okay, and then that together, all three are in series with R1. So R total is just in series with those like that. So we have R1, which is 5 plus 3.6. So our total resistance is 8.6 ohms. Therefore, we can then solve for total current. So we have 9 equals I total times 8.6. So I total equals not a great number. 1.0465. Yeah. Okay. So now we got to think about our circuit rules, right? So remember, these are the numbers for the battery. So is there anything in series with the battery? Yes, this isn't R1 is in series with the battery. Okay, so R1 is in series with the battery. So V total equals V1 plus V234, and I total equals I1 equals I234. Now we know what that the equals we can definitely take advantage of. So I total is 1.0465. That must equal I1, which also equal I234. Okay, so I1 is here, and that gives you 1.0465. Okay, I need to do that just to make it line up better. So now we have these two. This means that V1 equals I1 times R1. So we have 1.0465 times 5. Here, let me do 1.0465 times 5. Okay. 5.2325. I should round these up another level. Yeah, whatever. Screw it. It's just not going to look pretty. Too bad. Okay, so we have that. So that's V1. However, we have V total equals V1 plus V234. Okay, so V total equals 9 equals V1 plus V234. So 5.2325 plus V234. So therefore, V234 equals 3.7675. Okay, you might think, okay, well, who cares about that? Well, V234 is, right, that's the parallel piece. Okay, so the parallel piece, that's made of, in here, 2, 3, and 4. So in parallel, what's the rule for parallel? Voltage is equal for parallel. So since R23 is parallel with R4, V234 equals V23 equals V4. So, and that equals 3.7675. So, V4 is that. And then we can then work to find what is I4. So V4 equals I4 times R4. So we have 3.7675 equals I4 times 9. So I4 is, oh boy, 0.4186. Okay. Okay. So now, what's the current rule for things in parallel? So, parallel rule, I234 equals the sum, right? I23 plus I4. I23, do we have I23? We do. It's so I23 is the total here. So that is 1.0465 equals I23, which we don't have, plus I4, which we do have. So I23 equals 1.0465 minus 0.4186, 0.6279. Now, I23, though, that's in series, right? These two are in series. So therefore, the current rule for them being in series is equal. Okay. And we can then solve for V2 and V3. 279 times 4, 2.56. And V3 is half that, 1.2558. Very messy, but okay. Now let's see if, since we have the circuit built, our numbers line up with this. So here's the voltmeter, and here. So we want. I always forget which order do we want. Do we want this order? Okay. So V1 should be 5.23. 5.23. Okay, good. V2 2.51. Yep. Okay, V3. 1.26. Yep. And V4, 3.78. 3.77. Oh, yeah, 3.77. Okay, yeah. Okay. And total voltage is 9. Yeah, we got that. Okay. Current. Current 1 should be 1.05. Yep. Current 2 should be 0.63. Current 3 should also be 0.63. Current 4 should be 0.42. Yes, and then the total current should be 1.05. Indeed. All right, we did it. Numbers are kind of gross, but hey, that's what I get for coming up with this on the spot, right? So, yeah. Actually, things were actually not bad, except adding this to be plus 5, so that, like, this is 0.8, 8.6, and then, so 9, the fact that I do 9 divided by 8.6, that led to the current being gross, and that leads to all this stuff being gross. So, I guess, better thing would have been, I don't know, either have this be a slightly better number and have this be a slightly better number. Whatever, doesn't matter. Point is, I showed you kind of how to solve for this, so you can kind of see the strategy here. You definitely want to find R total first, and then you sort of got to think about it in terms of the voltage rules and the current rules for series and parallel, and just sort of kind of break it down through there. And it takes a little bit of effort, but you can do it. You can get to what you need to do. So those are kind of the main sort of questions I could ask of you, really. So not really too much else to get at. I mean, I could just do more and more examples. But again, you should kind of watch back on the videos and see the examples I've done before. You probably forgot the examples specifically in terms of stuff that's like, from like 3 weeks ago. But yeah, and of course, there's questions. If you have any questions, you can ask either through Discord or through commenting or through email. Yeah, and of course, you can ask each other, especially when you're going through the test. I don't think there's anything else to mention. Well, if there is, I'll post about it. So, okay, I guess that's it for that. And hope the test works out well enough. There you go.